Start the class. We are talking now, still talking about the machining. This is chapter 17, Fundamental of Machining. We started last time and we're going to continue today about the machining. The fundamental of machining. In machining, uh, as we discussed last time, machining, we remove part of material. We remove a layer of material. There are a tool and workpiece. Using the tool and workpiece or tool cut the workpiece to remove part of material. Remove mean cut part of material. When you cut part of material, you get the desired geometry. You get the desired geometry. So you remove part of material, then you get desired geometry. There are three fundamental items in machining, which is the cutting speed, depth of cut, and feed. This kind of relative motion between tool and workpiece. Without the relative motion between tool and workpiece, cut will not happen. So cutting speed actually obtained by the rotational speed of the workpiece. When the workpiece is rotating, this is a cutting speed. So cutting speed is the rotational speed of the workpiece. Depth of cut obtained by the tool. Tool here penetrate. Tool here, you can see that. Tool here penetrate to get the depth of cut. This is the whatever we call depth of cut. Depth of cut. You remember this kind of terminology. A tool penetrate here. So you can see that tool penetrate, as you can see here, tool penetrate to get the depth of cut. This is the depth of cut. Depth of cut is the difference between the initial diameter and final diameter. Then you get the depth of cut. When tool penetrate, you get the depth of cut. And feed tool must travel in this direction. Tool must travel in this direction. So here you can see that tool here, this is the depth of cut, and tool must travel in this direction. Tool must travel in, we call it longitudinal direction or axial direction. This is axial direction. This is a radial meaning radius. So tool in depth of cut, tool will move in radial direction to obtain the depth of cut, and then tool must travel in longitudinal or axial direction to achieve the feed, to achieve the cut or to perform a cut from beginning to the end. This is the speed, the tool travel speed in the longitudinal direction or axial direction is whatever we call feed millimeter per revolution. Millimeter per revolution mean every one revolution tool will shift millimeter. If you said, for example, 1 millimeter per revolution means that every one revolution here, revolution meaning rotation, every one revolution tool will shift 1 millimeter. Another revolution shift 1 millimeter. So this is the traveling speed in the longitudinal or axial direction. So three we call it is a cutting parameter or cutting condition, cutting speed, depth of cut, and feed. This is the three fundamental cutting condition. Cutting speed is obtained, as I told you, from the rotational of the workpiece. So rotation of the workpiece delivers a cutting speed. Delivers a cutting speed. Cutting speed equal to pi d, and d is the diameter. Because here v here is a velocity here. Velocity, this is a velocity. Let me just highlight. Velocity is here, linear velocity. This is a linear velocity. It's coming from the rotational of the workpiece. Let me highlight like this. Okay, so this is a linear velocity, which is a cutting velocity. This is a vector, cutting vector or cutting velocity vector coming from rotational of the workpiece. So this velocity, the velocity here equal to omega r, omega rotational angular rotational speed multiplied by r, which is the radius of this one. So omega r, right? Omega r meaning omega equal to 2 by n, then 2 by n r meaning by dn. So v, this is the v. See right here, this is the v, which is a cutting speed equal to pi dn. V equal to pi dn. This is a cutting speed. Depth of cut, as I told you, this is the depth of cut. Depth of cut happen when tool travel in radial. This is the radial direction. Tool move in radial direction to get the depth. The depth here is the difference between this diameter and this diameter. So it is d outer minus d final, or d initial minus d final, d outer minus d final divided by 2, because if you, the difference is this distance and this distance, so you divide by 2 to get, this is a depth of cut. So depth of cut is d outer minus d final divided by 2. A feed, which is a tool travel in this direction, this is a feed. Tool travel in axial direction or longitudinal direction with millimeter per revolution. Millimeter per revolution, the mean tool will move in millimeter per every single revolution. Right. Material removal rate or volume of material removal rate, volume of material, the volume of material being removed equal to VFD, VDF or VFD, meaning V millimeter per minute, F which is a millimeter per revolution, and D is millimeter, then cubic millimeter per minute. So cubic millimeter per minute meaning volume rate. This is a volume rate of material being removed every unit time. So VFD is a material removal rate or volume of material removal. Right. This is a discussion description. We have in metal cutting, we have what we call is independent variable, and we have dependent variable. Independent variable, which is a variable you set, or means the operator set at the beginning of the cutting. Operator set at the beginning of the cutting. Like what? Like cutting speed, feed, and depth of cut. As I told you, this value. What is the cutting speed? What is the cutting speed? What is the rotational speed? This is one. What is the depth of cut? This is two. What is the traveling speed, which is a feed? This three. This is kind of parameter independent, because we fix this parameter at the beginning. At the beginning, before we do the cutting, we decide what is the feed, what is speed, what is the depth of cut, what is the material that we're going to cut, steel, aluminium, and so on. What is tool material? What is a tool material? We can maybe use carbide tool, HSS tool, ceramic, whatever tool. Then tool geometry, tool material, tool geometry, workpiece material, cutting speed, feed, depth of cut, which you call it cutting parameter, characteristic of the machine tool. What is the machine we use? What is the rigidity? What is the stiffness of this machine? Work holder, how you holding the workpiece, how you holding the tool, whether we're using cutting fluid or not. This is whatever we call cutting fluid. Do we need to use a cutting fluid, or we don't use cutting fluid? All these parameters we fix at the beginning before we do the cutting. So we call it independent, because we can select as we want, right? So based on what we're going to do, right? So we call it independent variable or independent parameter. However, we have another parameter we call dependent variable or dependent parameter, and this dependent parameter or variable depend on what have been selected initially, which is, for example, force and energy and temperature. The force obtained here actually dependent on what? Dependent on what is the cutting condition used, what is the speed, what is the feed and depth of cut. A bigger speed and feed and depth of cut leading to force to increase and energy will increase. You see that it is dependent on what you select initially. So we call it dependent parameter. Temperature also, cutting temperature. Whenever you have a higher cutting speed and feed and depth of cut, temperature also will increase. Type of chip also, chip thickness. Chip, I mean the deformation of the material, how material will deform, how material will be cut, what is the chip type, what is the chip thickness. It depends on what parameter you select at the beginning, so we call it dependent parameter. Wear in the tool, wear and failure, it depends all on the initial parameters. So initial parameter determine or obtaining the whatever happening in the tool, with tool wear, tool fracture, and so on. Surface quality, that the surface finish obtained from the process, also depend on the parameter. So this is whatever we call dependent. So we have independent parameter, This independent parameters that we set initially before we do the cutting, and we have dependent parameter which is obtained later from the cutting and dependent on what we set at the beginning of the process, right? A second example, this is the lace operation. This is lace operation. Lace operation is a cylindrical shape cutting. Usually lace, we're going to discuss many actually operation. We'll start with the lace. Lace is, as you can see here, cylindrical shape cutting. So this is a tool, this is a workpiece. We're removing a layer of the material. There are several types of the lace operation. This one we call it straight turning. Lace or turning, same meaning. This is a straight turning, as you can see here. Tool will travel in straight direction. Initially, tool I get the depth to penetrate to get the depth of cut, and then move in linear direction. So call it straight cuttings like this. This is the taper cutting. Taper cutting actually, uh, 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 the only difference between taper cutting and straight cutting is that the tool here move in X and Y direction. In radial, tool moving in radial, here you can see that tool moving in this direction. Tool moving like this, not straight, moving like this. This mean in both radial, this is radial and also longitudinal in simultaneously. So you can see that taper tool here moving in both radial and this is the radial meaning in the radius direction, longitudinal mean or axial mean in x direction. So tool here moving in both radial and axial direction simultaneously. Also profiling also, tool moving in both directions simultaneously. This one we call it is the external groove. External groove is very similar to straight cutting or straight turning. Tool initially penetrate to get the depth and then move in this direction to obtain groove. groove mean يعني نعمل groove على السطح. Here facing mean tool will cut the face. This is a face. Then tool move only in radial direction because cut the face. So tool move in radial direction. This is a face groove. Tool here making face groove or groove in the face. Here, groove in the face. Here we said this one is a form tool. Form tool, the tool have certain shape. The tool approach the workpiece and create the workpiece profile at once. There are no axial direction, only radial. Tool will penetrate in radial direction to create the profile in the workpiece and no motion in axial direction or longitudinal direction. This one is internal turning. We call it boring or internal turning. Internal turning, it means that the tool will enlarge the diameter. Initially, we must drill. We must create a hole. We cannot do internal turning unless we create hole first. So first we need to drill to create hole, and second, the tool will get inside and then enlarge the diameter or enlarge the size or increasing the diameter size of the hole. Initially hole, and then the tool will increasing the dimension of the hole inside, right? So this whatever we call internal turning or internal grooving or boring. This is the cut off. Cut here. A tool penetrate in radial direction. All time penetrate in radial direction. All time penetrate in radial direction to separate. Cut off. We separate the part to two parts, right? This is the threading. Threading here, there are a special tool. Threading here, we have a special tool. This is special tool with around 55 degree or 60 degree. It depends on the standard. And this tool will create the profile here initially and then travel in axial direction to create the profile of the thread from beginning to the end. We call it threading. اللي هو الالوز يا شباب بالعربي، يعني الالوز اللي هو المسمار، يعني الثريد بتاع المسمار. Kerneling here means we make surface is rough. This is a rough surface to creating rough surface. This is a kind of roller. This roller to create the rough surface in a surface mainly for handling and so on. This is some processes in a lathe machine. Okay, let me show you a video, a nice video, to make this one clear, more understandable. Okay, right. Okay, let's see together. Let's see together. Please give me your attention, guys. Please give me your attention. I'm going to explain what we discuss here. This is a lathe machine. This is a lathe machine, right? Lathe machine, cylindrical. All time, remember, this is cylindrical shape. We cutting cylindrical shape in a lathe machine. You see that the workpiece is rotating. Workpiece all time here, workpiece is rotating, right? So workpiece is rotating. This is the tool. This is the tool. This is the face cutting. Again, one more time. This is a rotating. This is a single point cutting tool. This is a turning tool. This is a face cutting, radial direction. Tool move in radial direction. This is a drilling. We drill here. We drill here. Can you see that this is rotating? This is we drill. We create hole. This is internal turning. Internal turning, you see that we increasing the dimension. We make the dimension bigger. So initially we drill. This is a straight cutting. Straight cutting at different level. Now this is the diameter, big diameter, smaller diameter. So this is a straight cutting. Now we're removing material. We're removing material from beginning to the end, right? This is a taper. This is a taper cut. Taper cut here, you can see that move in X and Y. This is a surface. This is a face cutting. This is the taper. This is straight. This is a taper. This is straight. Can you see that? This is a straight cutting. Straight cutting. Straight cutting. Straight cutting. You see the depth of cut here. This is depth of cut. This is a depth of cut. So initially, tool penetrate to get the depth of cut and then travel. This is the tool traveling speed from beginning to the end to make this one. This is a thread. This is a thread. Thread here. This is the thread tool. This is thread to make threading which الراوز يعني يا شباب. Threading, we make threading in the outer surface. We make threading on the outer surface. Okay, now they need to cut here. We need to cut separate. We need to cut this part is already finished and need to cut here. Then initially we must rotate. This one must be rotated. Because cutting speed always obtained from rotational, so we rotate here. This is a cut off. Cut off meaning we separate. This one penetrate in always radial direction. Always, there are no axial. Always radial, radial. We penetrate and so finish. You cut here. Then you separate this part to twice. This is a cutting fluid. Then you can see here, this is a cutting fluid being used. Sometime being used, sometime not. This is a face. This is a face. Because this is a face now, face machining. So this is a facing. Okay, this is a face cut. Face, because here we cut a face in the radial direction. Here we drill, we create the hole. In the other side, we remove the material, we create the hole. Then hole will be extended now. And then now, this is the internal turning. Can you see that internally? See, so first we must drill. We must create hole. Second, this is the internal turning. Internal turning, the tool, you can see that inside, enlarging the side. Make this, this is the taper. Can you see that? This is the taper. This is straight. Whatever you do outside, you can do inside, actually. Whatever you can do outside, you can do inside. So now this is the hole. Now you do thread inside. This is threading inside. You see that you can do thread outside, you can do thread inside. So this is the threading inside. Right, so this is the threading inside thread. This is whatever we call internal turning. Right. And then you do here straight cut to remove this. This is the depth of cut, guys. This is the depth of cut. This is the feed. This is the feed motion. This is the feed motion. This is the depth of cut. This is the speed coming from here. This is the groove. We're creating groove. Only groove. We don't want this is the cut off, but here we use to make just groove. Just only you make groove here to separate this one from this one. That's it. We don't if you penetrate more you cut, but you don't want to cut, just make groove. Then this one is still remaining there. This is another multiple point cutting tool. I will discuss this later. Right. We get back to the slide again. Okay, then this is a cutting processes, lathe operation. So lathe operation, this is a straight cut. I hope you remember. This is a straight cut. This is the depth of cut. Tool initially penetrate to get the depth of cut. This is a straight cut, straight cut. This is the taper, right? Taper meaning tool move in both radial and axial direction simultaneously. This is a pocketing or profiling. This is a profiling. This is a groove, external groove. This is a cut off tool, but no need. They don't want to make cut. If you penetrate more, then you cut off. But here only make external groove. Here facing mean to cut a face. Here this is a face. Here tool moving only in radial direction, no axial, but only radial. This is the groove in a face. Here making groove in the face. This is the forming tool. Tool have a certain form, have a certain shape. Tool will penetrate approach in only radial direction to create the profile. This is the internal. Internal initially we must drill. We must drill initially. Initially we must drill. We make a hole and then the internal tool get inside to enlarge the diameter. Enlarge making the diameter is bigger. This is a cut off. Cut off here. This is a cut off tool. As you saw in the video, the tool will move in the radial direction until separates the two parts. We call it cut off. Threading here, you saw in the video outer and inner. You can do an outer surface or inner surface, mean external turning or internal turning can. This is special tool with certain degree, and then you can just create a profile, the thread profile. This is kerneling actually. We didn't saw in the video, but this is kerneling only to rough the surface, to make surface is rough, right? In a cutting, in machining, we have whatever we call rough cutting and finishing. Please listen to me carefully, guys. We have whatever we call rough cutting and we have whatever we call is finishing. Rough cutting, we remove big amount of material. We remove in rough cutting, we remove big amount of material from starting workpiece. We remove big amount. In rough cutting, we use high depths of cut and high feed rate. High depths of cut, high feed rate, and low speed. High depths of cut, high feed rate, and low speed. Because if you have high, then tool will be broken. Then high depths of cut and high feed rate to remove big amount. Then let me just get back to show you. Then this is a depth of cut, big depths of cut. Penetrate with the big depths of cut and big feed rate. Feed rate meaning the feed speed to move here is big, to remove big volume of the material. To remove both big volume of the material. But the cutting speed we use here is low. We use a low cutting speed here to not broken the tool. So in this case, let me tell you again, in rough cutting, we use high feed and high depth of cut and low speed. High feed, this is the one. High feed and high depth of cut or big depth of cut, but low speed to not broken the tool. This one to remove big amount of material. In a finishing is this is the next step. Initially, we start with rough cutting to remove big amount of material, and later we do finishing. Finishing actually we do finishing in low feed, low depths of cut, very small feed, very small depths of cut, but very high speed, cutting speed. This one to obtain a final dimension and the tolerance. We remove a small, very small amount of material, but we're going to get, or we would like to get the excellent finishing quality. Excellent finishing quality. Okay, let me get back to the video again one more time. Let me show you the video again one more time and discuss this point. Please give me your attention. Okay. Okay. You see that this is a big depth of cut. This is a big depth of cut. Can you see that? Now this is a rough cutting. This is a rough cutting. Can you see here? This is a big depth of cut. Big depth of cut. Big feed. Feed is high, depth of cut is high, removing big amount of material and the rotational speed, right? So you see that this is big, we're removing big amount. This is the rough cutting, we're removing big amount of material, right? Right. And now another tool, this is the tool for finishing. We use a tool for finishing. This is a finishing. I hope you realize this is the depth of cut. Can you see that? I'll show. You see, I'll stop the video. Depth of cut here is smaller. And can you see the difference? Quality here is low quality. Quality here is better, excellent quality. Why we have excellent quality here? Because we here using depth of cut, small feed rate. We remove the small. Previously, we were removing a big amount of material. We have very high feed rate, very high depth of cut. Depth of cut was big, and feed rate is big, and the rotation speed was low. But now we do what we're doing. Depth of cut is small. We're removing a small amount of material to get better quality or the best quality. Can you realize the difference between the rough? This is the rough cutting. This is the finish. See that? So you see that? This is the difference. This is the rough cutting. This is the finishing. Now when we're doing that, we get the excellent quality. And then finishing usually is the last step. Then get back again to slide. Then finishing actually, okay. Okay, in rough cutting, then again in rough cutting we do what we do in rough cutting. We do high speed and high depths of cut and low speed. Why was the benefits of rough cutting? In a rough cutting, we would like to remove big amount of material, to remove big amount to not waste the time, to reduce the machining time. Because the finishing usually take longer time than rough cutting. Rough cutting takes short time. Then initially, I start usually with several rough cutting to remove big amount of material with a shorter time, or shorter possible time. And later, we do one or two finishing to get the excellent dimension tolerance and surface quality. This is a low feed, low depth of cut, but high cutting speed. Right. So this is describing the situation. In the rough cutting, as an example, feed equal to 0.4 to 1.5 or 1.25, depth of cut 2.5 to 220. This is the rough cutting, but when you come to the finish, can you see the difference? Feed 0.125 to 0.4. This is very low feed compared with the feed here in the rough cutting. Depth of cut also 0.75 to 2 millimeter is small compared with here. Here, the rough cutting speed, the rotational speed in the rough cutting is smaller than in a finishing. We have high speed, very high speed. In the rough cutting, we usually reduce the speed. Right? Did you get it? Did you get the difference between rough cutting and finishing? And is the reason? So usually we start with several rough cutting and then followed by one finishing process. Right. Next, we're going to talk about the mechanics of machining. Mechanics of machining. Okay, mechanics of machining. This is machining. Machining is like this. This is a turning operation, but I rotate. Horizontal, by I rotate, make it vertical, right? So you can realize what I'm telling. This is a tool and this is a chip. Tool here removing chip. This is a chip and this is a workpiece. This is a tool actually. This is a chip. This is a workpiece and tool removing chip from the workpiece. Actually, let me tell you, this is a cutting. Usually, it is in 3 dimension. Cutting usually or cutting always in 3 dimension. This is the cutting that we have, right? However, for simplicity, they do analysis in 2 dimension, not 3 dimension, but 2 dimension. So this is a tool, this is a chip, and this is a workpiece. So it is in 2 dimension. Always they make analysis in 2 dimension. Why? Why 2 dimension? To make it easy, to make it simple. Because finally, what you're getting is kind of approximation. Approximation. Whatever analysis you do, you get approximation of solution. So they usually do in 2 direction, not 3 direction, but 2 directions. You call it orthogonal cutting. So orthogonal cutting, it means that 2 dimension analysis. Remember this. Then simplify the process into 2 dimension called orthogonal cutting. Orthogonal cutting is a 2 dimensional cutting. Orthogonal cutting is a 2 dimensional cutting. This why? Because of simplicity. Right. When you're coming to the tool, this is a tool, right? This is a workpiece. This is a chip coming out. This is a tool. This is a workpiece. This is a chip here being cut. Right. Okay, there are some important terminology. Please give me your attention, guys. Please give me your attention because this is really very important. This is the rake angle with the vertical line. This is a vertical line. Can you see that? This is a vertical line. This is the rake angle, tool angle. We call it rake angle. Can you see that? This is the tool angle. This alpha. This alpha. This is the rake angle. And the alpha D, this alpha, here is 0. Alpha here is 0. At this is 0, right? At this line is 0. Here positive, this is positive alpha. This is negative alpha. So positive alpha, this is negative alpha. We call it rake angle. So alpha is rake angle, right? This is the tool. The blue here is the tool. This whatever we call the relief angle or clearance angle. This clearance angle important to keep the tool away from the machined surface. This is the machine surface. And this angle important to keep the tool away from the machine surface. This is a chip. Can you see that? This is a chip. This is here. Let me highlight. This one we call it shear plane. Why we call it shear plane? Because here the chip, this is a chip. The material here, the tool here, tool shearing the material here in this plane. As you can see here, so material is tool pushing, tool moving in this direction, tool moving in this direction, right? Tool moving in this direction. Can you see that? Tool moving in this direction. When tool moving in this direction, pushing material. Material will be sheared here, like this. See, this is the actual photo. This is a tool. This is a workpiece. This is the actual photo. Then you can see that the chip will be sheared here. We call this one shear plane. This one we call it shear plane. I hope you remember what I said. This is the shear angle. This is the uncut chip thickness. Uncut meaning not cut yet. Not cut yet. TO is the uncut chip thickness. This is the TC. TC is the cut chip thickness. Means that already cut. Phi here is a shear angle. This is a shear plane. Phi here is a shear angle with the horizontal line. We call it shear angle. This is the terminology here. This is the terminology in the orthogonal cutting. Remember orthogonal cutting. This is the terminology in orthogonal cutting. Any question? Right. This is a description. You can read it. So that's what I'm just exactly said. Relief angle, shear angle, and so on. Right. Here, start analysis. We have whatever we call cutting ratio. We have whatever we call cutting ratio. Cutting ratio equal to R. Cutting ratio equal to TO. which is the uncut, remember all time, uncut chip thickness divided by TC. TC is the thickness here, which is the cut chip thickness. This one equal to phi, this angle sine phi shear angle divided by cosine phi minus alpha. Cosine phi minus alpha. From where is this one obtained? From where is this one obtained? Let me show you. Okay, let me show you. This is a tool. This is the tool. Just please give me your attention. Please give me your attention. This is the TC. This is the TO. TO, this is the TC. You know that R equal to, here R equal to TO divided by TC, right? You agree? Then R ratio, cutting ratio equal to TO divided by TC, right? Then here, let us see how to apply to obtain this equation. Let's see. This is the AB between these two. This is the TC, this is the TO, this is the phi, this is a phi, this is alpha. If you make vertical line, if you make vertical line here, this is the vertical line, right? If you make vertical line like this is the alpha. This is alpha. Right, this is alpha, this is the vertical line, this is the rake angle, this is the phi, this is phi, shear plane angle, this is rake angle, this is the TC, this is the TO, right? This is the AB, shear plane, this is the AB, which is a shear plane. This angle, the angle here, this angle is phi minus alpha. This angle here, can you see that? This angle here, this one is phi minus alpha. Then when you come to AB, AB equal to what? Can you see that? AB equal to, this is the diagonal, right? This is the AB, AB. This is the right angle, this is the right angle. So this is right triangle, this is right triangle. Then sine phi here, start with this one, sine phi equal to TO, sine phi equal to TO divided by AB. Sine phi equal to TO divided by AB. And here also cosine phi minus alpha, this angle, cosine phi equal to TC divided by AB. Then AB here and AB here. This is the sine phi, this is cosine phi minus alpha. Then you need TO divided by TC. This is the TO, this is the TC. Then TO equal to AB, this one. TC equal to AB, this one. When you divide TO by TC, this is the TE. AO sine phi divided by TO equal to AB sine phi, this is AB sine phi, and TC equal to AB cosine phi minus alpha. Then AB go with the AB, then sine phi divided by cosine phi minus alpha. Did you get it? Then cutting ratio TO divided by TC equal to sine phi divided by cosine phi minus alpha. Muhammad, yes, I am listening. Muhammad, yes.
What is TC?
TC is this is the thickness, cut chip thickness. This one, cut chip thickness. This is the TC. Did you get it? TO uncut chip thickness. TC is the cut chip thickness. يعني سمك ال TC هي دي. سمك الرايش يعني اللي طلع أو الشيب اللي طلع. Did you get it?
Yes, okay.
Actually, this one can be measured. Actually, this one can be measured. How we can measure TO? We know. TO we know because initially we set this TO, which is uncut chip thickness. We know this one, right? TC, how we can know the TC? Actually, TC can be measured. How we can measure? When you do the cutting, you take the chip and put under microscope, you get the thickness. So we usually measure the TC. We will be able to measure the TC. Is it okay? Then R equal to TO divided by C equal to sine phi divided by cosine phi minus alpha. Rearranging this one, rearranging this equation, we can obtain tan phi, which is phi is the shear plane angle. Tan phi, this one, tan phi equal to, from this equation, rearrange this equation, tan phi equal to R cosine alpha divided by 1 minus R sine alpha. This is the tan phi. From this equation, based on r and alpha, we can obtain phi. We know r and alpha. We know r and alpha. Alpha is the tool angle. Whenever you have the tool, you can measure this one, then you know alpha. Then we have tool angle, we know alpha. Then alpha we know. R also we know, because TO we know, we fixed at the beginning. TC we can measure from the chip, then we know TC, we know the TO, then we can obtain R, then we know R, we know alpha, then we can obtain phi. Phi we cannot obtain, we cannot measure, but we can obtain the based on or with respect to R and alpha from this equation. This is a shear plane angle. Right? Any question? Any question, guys? Right. So next is speed velocity triangle or velocity ratio. Velocity triangle or velocity ratio. Let me tell you how to draw the velocity triangle. Guys, please give me your attention. Please don't do anything. Just focus with me here. Just give me your attention, please. This is whatever we call velocity triangle. How many velocity vector we have? We have three velocity vector. This is one velocity vector. This is the second. This is the third. This one is a cutting speed vector. Please give me your attention, guys. Please give me your attention. This is a velocity vector, cutting velocity vector, horizontal one, because the tool moving in a horizontal direction. This is a chip velocity, because chip moving in this direction, chip coming like this and move in this direction. So this is a chip velocity, we call it VC. Let me highlight. This is chip velocity, this is a cutting velocity, and this is the shear velocity, 3 vector. Shear velocity, because the material will be sheared in this direction. So this is a shear velocity, this is a chip velocity, this is a cutting velocity. Right? You plot, this is the V horizontal. You put V horizontal, right? You put V horizontal. This is the VS. VS, which is a shear velocity. This one. The angle here is phi. Yes, this is correct. Because the angle here is phi. This is a phi. Then phi with the horizontal. If we know phi, this is the angle phi. Between what? Between the VS, between the horizontal and this one. Then here you put this one VS. This is angle phi. Right. This is the V chip. V chip here, this is the VC. VC will close the triangle. What is the angle here? The angle here actually, let me tell you, if you make a vertical line, this angle is alpha. You agree? So this angle is alpha. So alpha with the vertical. Alpha with the vertical mean this one is 90 degree. This is 90 minus alpha. So this is phi. This is 90 minus alpha. What is the third angle? Third angle is 180, because the summation of the angle, triangle angle, is 180. So it is 180 minus phi minus 90 minus alpha. So I can write it this way. It is 180. This one is 180. This is the total angle of the triangle minus what? Minus phi. How to write phi? I write in Roman letter phi minus, open here, 90 minus alpha. Minus alpha. Can you see that? Okay. So this is the angle actually. So this is the angle. This angle is 180 minus phi minus this one. This is a phi. Let me highlight. This is a phi. This is a 90 minus alpha. Then you get the third angle. So this one minus 90 plus alpha, because minus meaning plus. So minus 90 plus alpha. Then it will be 180 minus 90 mean 90 minus phi plus alpha. Did you get it? So this is the one actually. So this is the angle here. So it's three angle. So this is the Vs, this is the V, this is the Vc, which is, this is a chip velocity. Remember, chip velocity. This is a shear velocity. This is a cutting velocity. This is alpha. This is phi. This is 90 minus alpha. This is 90 minus phi plus alpha. Any question? Right. There are rules here. There are rules here that every speed divided by, from the velocity diagram, you see that? Listen to me carefully. V divided by the corresponding angle, sine of the corresponding angle, V divided by sine 90 minus phi plus alpha. It is minus phi plus alpha, because minus minus get plus. Then V divided by the corresponding sine of the corresponding angle, sine 90 minus phi plus alpha, equal to Vs divided by sine 90 minus alpha, equal to Vc divided by sine phi. Did you get it? Then every velocity divided by sine from the velocity diagram, every velocity divided by sine the corresponding angle. This one equal to V divided by sine 90 minus phi plus alpha, equal to cosine phi minus alpha. Vs divided by sine 90 minus alpha, equal to cosine alpha. Same, sine 90 minus alpha equal to cosine, sine 90 equal to cosine, sine phi being sine phi, because it is exactly sine phi. So sine phi, this is the triangle from the velocity triangle or velocity ratio. So if you know any speed, you can obtain other. Actually, I don't know what is the Vc and Vs. All time, I don't know what is the Vc and Vs, but I know cutting speed. So if you know the cutting speed, if you know phi and alpha, then you can obtain Vs and you can obtain Vc as function of V and angles. Is it clear? Any question? Guys, any question? Right. Shear strain. Shear strain, usually material initially deformed. When the tool push, material will be sheared. But before shearing, material will be deformed. If you realize here, there are initially plastic deformation. Initially plastic deformation. And then shearing. At maximum deformation, when material reach to the maximum deformation, material will start to shear and separate. This is what we call shear strain. So shear strain usually is a deformation, the maximum deformation divided by the initial length. When you reach to the maximum deformation, shearing will happen, material will start to separate, chip will be obtained. From the geometry, actually, this one I'm not going to spend time to show how this one obtained, but this one obtained from geometry actually equal, because it is not shown in the book and actually need some time to do, but no need to describe and show how we can obtain gamma, which is a shear strain. This is a shear strain, as I told you. This is the shear strain, which is gamma, equal to tan phi minus alpha plus cotan phi. Tan phi phi is the shear angle minus alpha is the tool angle plus cotan phi. This is the shear strain obtained based on the deformation, as I told you. So this is the shear strain. Okay, let's take an example. Let's take an example. In machining operation, the approximate orthogonal cutting. Orthogonal cutting means two-dimensional cut. The cutting tool has rake angle. This is alpha is given. This is the rake angle. Chip thickness is given. TO is the uncut chip thickness, and chip thickness after cut TC is given. Then he give me TO, TC, and alpha. Calculate the shear plane. I need to obtain phi, and we need to obtain the shear strain. Then first R equal to TO divided by TC. TO is given, TC is given. This is R ratio. And then you apply in the equation tan phi equal to R cosine alpha divided by 1 minus R sine alpha. Then tan phi equal to R, this is R, cosine alpha is given 10, divided by 1 minus R sine alpha. Then you get the tan phi, then phi equal to 25.4 degree. Shear strain, what is the shear strain? This is shear strain is a dimensionless. Then you can obtain as tan phi minus alpha plus cotan phi. Then tan phi is obtained here, minus alpha, which is 10, plus cotan phi. Then you can shear strain is a ratio. It is 2.386 deformation ratio. This is a shear strain, right? Okay, chip morphology. Actually, time is just finished. And then before we go, let me just take attendance. Last time attendance, please check your attendance. Okay, guys, this is a machining. Actually, let me tell you that this chapter really is very important. Then I hope you just give me full attention while we having a discussion